Welcome back. So let us examine Taylor and Maclaurin series. What do we mean by series? Now we know. Now we have a separate course on sequences, series, and power series, where we will discuss these concepts extensively. But series simply means the sum of the terms of a sequence. Okay. Basically, when we use the word series, we usually refer to infinite series, which means that the terms continue infinitely. Now, how do these come into play here, and how do these relate to Taylor and Maclaurin polynomials that we've considered before now? We know that from what we've done, we said that the function f of x is approximated by uh, those polynomials. So it's approximated by Pn of x, which could either be the Maclaurin polynomial or the Taylor's polynomial. I mean, I've said they are the same. I can call it either of them. Sorry, they are the same when x equals to zero. Sorry. So I can just generalize it as Taylor polynomial. Okay. So we know that f of x is just approximately equal to this. So far n is finite. Because even if we take our n to be 20 or even 100 or 1000, it is still an approximation to the function. That is, it is still not exactly equal to the function. So the only thing we can be certain of is the fact that f of x then is going to be equal to the polynomial Pn of x plus some error. There's going to be an error always. That is, there's always going to be a difference, no matter how small, between Pn of x and n of x. Of course, we know that that difference will become smaller and smaller the bigger our n is. But we call this En of x. That is the error associated with the nth degree polynomial approximation for f of x. So we know we can analyze what the error could be and all of that, but we that's not really our business here. But the point is that we know that the error is going to vanish as n approaches infinity. So what we know about the error is the fact that the error will be vanishing as n approaches infinity. The limit of this is going to be zero. That means that if we take infinitely many terms, that is, our n is infinitely large, then Pn of x, that polynomial, is going to be equal to the function. So, of course, we cannot realistically have infinitely large terms because that will not be realistic in the sense that, I mean, we cannot plot that. We can't say that this is what infinity is or that. So that is not feasible. We're just theorizing here. We are just developing some theory about it. That in fact, if it was possible for us to write out all possible terms, all terms that we can ever come across, so then it will be equal to the function at that particular point. And of course, it is not possible. So there will always be an error term, okay, associated with the nth order polynomial, okay, nth order Taylor polynomial of f of x, if you like. So that is the point here. So to take care of this, if we want to have an exact expression or an exact representation of the function f of x, then we should consider taking our n to infinity. That is, we should consider taking the summation from k, we wrote k earlier, from k equal to 0. Instead of stopping at n, let us take it to infinity. That is, let us write out all the possible terms because we know that as n becomes very large, this error is going to be 0. So if we don't want to have zero error, that is, if we want f of x to be exactly equal to our polynomial, then we should take all possible terms that we can imagine. That is theory, not practical. Okay, so we know that for our Taylor polynomial, this should be x minus x naught to the power of k divided by k factorial, then into the kth derivative of f at the point x naught. So we call this series. This is a series now. Series simply means infinite series. So it's an infinite sum. When you have an infinite sum like this of terms, you can call it infinite series. Once it is defined by some expression that changes or some number that changes for different terms. Okay, so for the first term, our k will be 0. For the next term, our k will be 1. And for the next term, our k will be 2. And then that continues like that. So we call this the Taylor series expansion of the function f of x. Okay, the difference between the Taylor series expansion and the Taylor polynomial expansion is that the Taylor series expansion goes to infinity. The Taylor polynomial stops at some n, or some natural number n. Okay, and the Taylor series expansion will be an exact representation of the function f of x. We know it continues forever. All right. And equivalently, if we're interested in the Maclaurin series expansion, that will be specifically for when x naught is 0. At x naught equals to 0, then we're going to obtain this result. The summation, of course, still to infinity from k equal to 0 to infinity, and the expression instead of x minus x naught, that will be x minus 0, and that is just x to the power of k divided by k factorial, then multiplied by the kth derivative of f at the point 0, since x naught is 0, and we'll call this the Maclaurin series representation of the function f of x. So again, these are just conceptual differences. Okay, the method of analysis is exactly similar to what we have done to obtain the Taylor polynomials. Okay, the only difference is that when we are doing the Taylor series or Maclaurin series, we will not stop at any definite value. We just put dot 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 here to tell us that this is an infinite series, so it continues till forever. All right. So that is that about that. When we get to the next lesson, we'll begin to examine examples and see what we call Taylor series expansion of different functions. We already have an idea what they will be. It just means that we will extend the Taylor polynomial to infinitely, we extend it infinitely. And with that, we come across the Taylor series and the Maclaurin series as the case may be for x naught equals 0. All right, thank you for watching. We'll proceed from here in the next lesson to actually work on specific examples.